Welcome. In this, the second part of our collision detection and response demo, we actually want to have a look at the collision elements in terms of how the player moves, detects collision with other objects, and then responds appropriately to that particular collision. So largely we'll be having a look at our player sphere class and also our collision detector class. And we'll start off first of all with the player, just to go through how this particular one works. So it's a type of sprite, and a sprite is a type of game object. So these are ones that we notionally have sort of provided within our framework. Sprites are objects that can have an acceleration and velocity, be it linear in terms of movement or angular in terms of rotation. So this is something that we actually allow to move, to rotate. Now I say that, and there's a little bit of sort of smoke and mirrors in terms of how this particular demo runs. This gives the appearance of being a ball that is rolling and rotating around. And if I can jump up here, but you'll notice that as I move across, I can get to a point where the ball notionally is over the side. So what we are actually doing in terms of the collision detection within this here, it is still square, it is rectangular. So we have bounded our sphere or our circle within a rectangular bound, and we're comparing that rectangular bound against the other rectangular bounds of our platforms within this. So it's I suppose it's important just to understand that whenever the square goes off, then the thing will actually fall down. So this might look like a rotating object. From the perspective of a collision detection, it's not. It is a square rectangular bound. Its axis aligned. It doesn't change. We're just simply having the rotative bit by way of giving the appearance of a ball that is moving. But in reality, it's just rectangles is the only thing that we are considering here. It would be reasonably easy actually to extend this if you wanted to have a rectangular bound and a spherical bound. It's fairly easy also to work out if a a circular bound in this case in 2 dimensions is in contact with a 2-dimensional rectangle. That's not a difficult thing to incorporate. So we have our player sprite. We're defining a few values. Gravity. So the player actually contains the gravity value. Swings and roundabouts as to how you do this here. Within this here, the player is the only object or entity that there is. If you had a game with multiple entities that were all subject to gravity, it would make much more sense then to have gravity declared to be something within the world or the level. So it's here, it puts in a restriction that gravity is something that each entity gets to decide itself in terms of its strength, and you may or may not want that depending on your game design. We have our run acceleration. Now there's a few things here. This is the acceleration with which the player can move along the x-axis. If we went back to our sprite class, which was within our world folder in here, it defined a number of things for maximum acceleration, maximum velocity. And you could control and configure what these things actually are, be it linear or angular. So you might be going, given that's the case, given we can specify these maximum values, why are we creating more in here in terms of max x velocity, run acceleration, when we have ones available in our underlying class, the underlying sprite class? The reason for that is it's simple, but it just comes on to the types of assumptions. The sprite class assumes that things can rotate and accelerate and move in any direction with the same maximum value, so that I can accelerate up with a maximum acceleration, which is the same as my maximum acceleration, which I can go along to the side. Inside this game, that isn't the case. I want to define a maximum speed that I will allow the the ball to move along the x-axis, and that's what was it, 200 units. But when the ball's falling down, I don't want to restrict it to have 200 unit maximum velocity in that sense. So I'm having a setup where I have a maximum speed I can move to the left or the right, but I don't have a maximum speed I can jump up or fall down. So it's differentiating between sideways and up and down movement. But that quite often is important in a platformer. So my maximum velocity move along the x or the y-axis is, or sorry, the x-axis left or right is 200. My jump velocity, so anytime I hit jump, I'm setting an instantaneous y velocity of 450 up the way. So you see actually it would exceed the maximum if we put it in. And that works, so when you jump you get a sudden acceleration upwards, but gravity then is working to decrease that. So when it jumps up it slows down, stops, and then eventually falls down the other way. And that's the effect of the accelerative force that gravity is providing to bring it back down. Run decay, so this determines that as I'm moving along, so as I'm running this way here, I let go. The ball doesn't stop immediately, rather it slows down and then stops. So this is my run decay. It determines how quickly or how slowly I will decelerate down to 0. And if it were, for example, 0.99, then it's going to be initially like a more slippy surface. It'll take me longer to slow down. If it were, say, 0.7, then I would come to an abrupt halt fairly quickly. Angular scale. As this ball moves, it rotates. And basically, the faster the velocity, the quicker the rotation is. And I had a simple scale value here so that if you take the velocity and basically the speed, and you multiply it by the scale value, it gives you the angular velocity. So that the angular velocity kind of looks right. That it doesn't look to be rotating too fast or too slow, but reasonably decent rotation for the visual movement. And this is just simply a factor that will determine how I scale the speed into an angular velocity. So I picked it so that it actually looks reasonable in terms of the on-screen view. So there are a few different properties that control how the object moves or interacts. I've got my constructor. All I can do in the constructor is I pass things into the superclass. So when I construct a player, I say, where do you want to be started? You start X, you start Y, and what screen do you belong to? I then call the superclass constructor. Now it's going to be the Sprite one, but ultimately get passed up to the game screen, where I'm passing in the X and the Y. I'm giving this class an assumed size, so it's 50 by 50. And if you want to be proper, ideally I should have declared these things up here as properties that I could change at the top and then have it filter through in terms of the underlying code. Here I have my, the next thing I have to pass in is the bitmap that I'm going to use for this particular object. So I know the bitmap, or rather I know that the asset manager will have loaded the bitmap in. So I'm a game object, I go to my game screen, I get the game, I get the asset manager, and I get out the bitmap called ball from that one and pass it down. And then finally I pass into the superclass constructor, well, what screen I'm a member of. Player then has an update and has a check and resolve collisions, which is really called from the update. There's no draw as part of this, which means to say that the draw that the sprite cast comes along with, because my player sphere is a type of sprite, I'm perfectly happy with that draw method. I don't need to add and change any behavior, so I'm just going to use it and inherit it by default. So the rest of the stuff then is to deal with how do we update the player. So we're saying that we always have a downwards, so it's in the y direction, a gravitational value, which is trying to pull the object down. We're then checking to see, so remember for update, we pass in the time, and we pass in, are you moving left, moving right, are you jumping up, and give me a list of other objects in our world. So here we are checking, has the player provided us with input? So if the player wants to move to the left, but doesn't want to move to the right, then we will accelerate in the X direction. If the player wants to move to the right, but not to the left, then we'll accelerate in the right direction. If that's not the case, so either the player hasn't indicated either of those, or has clicked on both of them, which is a bit weird in terms of moving left and moving right. So in either case, none or all, what we say is that we won't move along the X, or we're not going to accelerate rather along the X-axis, and we will reduce our our X velocity by the run decay. So no acceleration, and you reduce your velocity in the X direction, so you slow down to a stop. That does the left and right. We have a check here for jumping up. So if we want to jump up and the velocity is equal to 0, then we set the y velocity then to be the jump velocity. So why do we have these things? So for example, if I were to, let me just comment. If I were simply to say, okay, if you want to jump up, then just set your y velocity upwards. And if I were to run this particular one, we can see what impact it will have. So we fire it in. So now if I hit jump, I just keep jumping up to the top of the screen. So I touch it, and I can jump mid-jump if I want to. So in this sense, I'm allowed to jump any time I want to. Which, depending on the game, you might want this here if it's a, I don't know, Flappy Bird type of thing. But most platformers, you only want to jump if you are if you're on a surface. You're not really jumping, you're not falling down. So this is the reason we put in the additional check here to see that if the user wants to jump up and my y velocity is 0. So, I removed it. So I'm not moving up, I'm not moving down. In that case, then I'm happy to jump. There is a limitation of this, but it's sort of 1 in a 1,000 limitation. But nonetheless, or nevertheless, you might want to sort of code it properly in terms of taking this into account. So I'm going to have to restart this particular one. I had to crash. The limitation that we're talking about here is the restriction that the y velocity be 0. And if it is 0, then we are prepared to jump. Why is it a problem? It's a problem because if I'm standing on a platform, then yes, my y velocity is going to be 0. But as I jump up, I'm going to be moving upwards. My y velocity will slow down, it'll stop, and then I'll fall down. So at the point at which it stops, the y velocity will be 0. So it is actually possible that if the player were to time everything remarkably well, just right at the top of their jump, they could manage a double jump. Now I'm trying to do it here. It's extremely unlikely to happen because we're doing it maybe 30 frames a second. You're likely to miss that exact instant at which the velocity is truly 0. But theoretically, it is possible when I'm running this here that it could be, and I could actually do a double jump, but very unlikely to happen. If you're going to do it properly, though, you would still really be changing this. If your player wants to jump up and you've had a collision with a platform, so you're standing on something, then yes, do permit jumping up to happen. Angular velocity then. So this is the angular velocity. It says, okay, what speed are we moving along the x-axis? And we simply scale it by our scale value. It gives us our angular velocity, and that was picked so that it looks natural. We don't seem to be rotating too fast or too slow. So we've done all of our setup here. We've looked at our input, we set up gravity, we checked it for jumping. We then call our superclass method. So Sprite class has an update method which takes into account the accelerations, the velocities, and updates all of these different things. So we've done all of our setup. We're now at a point where we can say to the under base class, okay, can you update my position, my rotation? And it will duly do that. A few then things that we want to check after that. First thing we want to check that, okay, so we probably applied an acceleration. Have a check that if we are now moving faster than we want to, not in the y-axis, but along the x-axis. So here we're checking to see if the absolute velocity along the x-axis, the speed, if it is greater than or maximum 1, then we're going to scale it back to the maximum, either minus or positive, depending upon the direction. So this makes sure we can't travel too fast along the x-axis. And then finally down here, because we've moved, we want to check to see, well, have we tried to move into a platform? Are we now in collision with something? So we want to check for that and to resolve it. And resolving in the context of these things here means that you stop it from moving, you set things like the velocities to 0, and you move it apart so that it's just touching and no more. So that's what we're going to be looking for. So check for and resolve. So we have it down here. It's a reasonably small method. Now there's a few. We're going to be having a look at our collision detector in a second. It's going to have a method determine and resolve collisions, where you can pass in an object and another object, a platform. So we're going through each of the platforms that we have within our level, and we're working out, are we in collision with that particular platform? This is not efficient. And the more platforms you have, the less likely it is you want to use a simple approach like this. Ideally, if you have 10,000 platforms, you'll go through all 10,000 platforms checking to see if you have hit the player. But the reality is there's only going to be a small number of those that are close to the player, probably, depending upon your game. So there are lots of different ways that you can more intelligently select the close platforms from it. They're sort of known as scene graphs, but they're maybe not slightly out of scope for the module that we're looking at. If you're doing a grid-based setup, then that gives you a very easy way of managing it. Anyway, this method, when we call it, it will tell us if we've had a collision, and it will also resolve, it'll also move the object so that it is not in collision. It'll move it so it's just touching. And we'll have a look in a little bit about what that does. This isn't sufficient. After this then, we are then checking to see what type of collision did we have. And if it was at the top or the bottom, we are setting the y velocity to be 0. Now let me take these things out. So what we have in there is actually not only changing the position, here we are also changing the velocity. Well, I've now commented it all out, so in reality, at the minute all we're doing is changing the position, and we're letting our velocity be whatever the velocity was. So let's run this here and see the effect that it has. So I run the game. Looks okay, and then the ball, actually the ball now is the bottom of the boxes, because it can never leave the screen, so we've positioned it down at the bottom. So what happened there? Run it again, got my ball here, oh, now it disappears in the bottom. I don't touch anything, it'll disappear down on the bottom. So we seem to have a fundamental problem. But whenever I put in the checks on my velocity and set the velocity to 0, that disappears. Now, the problem we have here is that we are applying an accelerative force, gravity. Now, an accelerative force will increase the velocity, so the velocity will get faster and faster and faster and faster. If I'm in collision with the box, I need to set the velocity to 0. I need to say that you have 0 velocity. If I don't do that, then the velocity is still continuing to increase. Now initially, the velocity is at a speed where each frame I may be moving 1 pixel down, then I may be moving 3 pixels down, then I'm moving 7 pixels down. So the faster it's going, the bigger the jumps are from one update to the next. Eventually, it's going to get sufficiently fast. The jumps from one update to the next are large. We're going to get to an update where the jump is sufficiently large that it's going to actually bring me completely under the platform. So if I don't change it, the speed's going up. I'll get to a point where eventually I will just jump straight past the platform. And obviously, that's not what we want to have. So there we are checking to see if we collide at the top or the bottom, set the y velocity to be 0. This is a bit superfluous because in this particular game we don't have any upwards velocities that are too high because gravity is acting to increase the downwards velocity. Now what about these ones here, the left and right ones? They're actually commented out. Let's put them in. So in this case we're saying that if we hit the left or the right hand side of something, we'll set the left or the right velocity to 0. So let's have a look at what that will do by way of our demo. And it's not ideal. I talked earlier on that having a big list or line of platforms at the bottom is not a great way of managing this. The reason for that is that, let's see if I can do it. Okay, actually I've done it there. It will disrupt the movement. So this is moving across. You may have seen it sort of stumble or stutter. There, it has stopped. Now I can still move it. I'll try to move this way here. It's stopped. When you have a collision, and we'll look at the collision detector in a second, you need to work out what side has collided with the object. Is it the bottom or is it the side here? And if I have my particular, in this case, sphere moving across, then I'm going to, and I have gravity pulling it down as well. I have it moving in two directions, so I can get into a situation where I will be potentially colliding with the side of this object because I'm moving in this direction, and potentially colliding with the bottom of the object because I'm falling down as well. And when we have a look at the collision detector, you'll see that it's the size, how much overlap there is, that will determine if I consider this to be a collision with the bottom or a collision with the side. So the fact that I get stuck at this particular point, I'm not pointing a different point there, is because I'm having a collision where it thinks the box is collided with another one on the side, which obviously it hasn't. Over here, fair enough, we are actually colliding with this particular one. So there's a couple of ways of getting around that. I mean, one is as was done here, simply don't change the x velocity. The other one, as opposed to having a big list of platforms along the bottom, you rather have one continuous or one large rectangle that isn't broken up into lots of smaller pieces. On large rectangular platform, again, you're not going to have this issue at all, and you can then put that particular blocking velocity in. So that's our player. Last thing we want to have a look at is our collision detector. And this, I'll go through it reasonably quickly, is based on a lot of the theory that we looked at within the lecture. It's not a huge amount to say in terms here, and it is fundamentally set up or assumed to be bounding boxes as opposed to spheres or circles. So if you wanted to use circles, again, you can enrich this particular one. So we have a enumerated type, which we use to indicate to a caller what part of us has been in collision. Is it collision with the top of us, the bottom of us, the left or the right, or if there's none at all? A few methods in. They're all static methods. So the idea is you don't actually create a collision detector, rather it is a collection of useful methods that can be called. So they're all static. So this one here is returned simply a true-false. Are we in collision? Takes in two bounding boxes. Where bounding boxes, they have a center point, they have a half width, a half height, and this one works out, well, do they overlap? Yes or no? Next method within this then is one where we're also taking in two bounding boxes, and we were returning a bit more information. It's not just if I'm in collision, but what bit of me is in collision. So I check to see, well, am I in collision? If I'm not, then I'm saying there's no type of collision. If I am, then I have to work out, and we're doing it down here, what type of collision that I have. To do this properly, or to do it accurately, you would have to look at how the objects actually came together in terms of their velocities. We're using a different approach here, but it's one that works well if the frame rate, or if the amount of space or distance that each object can move in an individual update isn't too large. What that means then, if two things come together, they will just overlap and not much else. So maybe I can run this to talk a little bit more about it. Okay, so we're going to have a situation over here that whenever I collide into the box, I'm going to be overlapped with a little fragment of the box. And we've got a quandary because all I get to see is the collision after the collision has happened. And all I'm working out is a rectangular region that I've overlapped with. In terms of how this particular object collided with this particular object, it actually could have happened in a number of different ways. I could have been falling down particularly fast. And in the last frame I was here, now the last frame I've fallen down into the object by that amount of distance. I could have been moving in this direction, where I have entered into the object by a small amount of distance. I could have been travelling at great speed along this direction, sort of jumping big distances between each update. And then I've travelled all the way through the object and I've just nearly left it on the other side. So for collisions, it depends upon the direction in which they've come together. As long as you're doing a fast frame rate and as long as the speeds are not too high, then what you can assume is that when I collide with something, I'm going to check to see what's the overlap in this direction, the overlap in that direction, and that direction. I'll get potentially distances in each of those directions. And whatever one has the least amount of overlap, that is just overlapped and no more, that's the one I assume that has just happened. That has been the direction of impact. And it works remarkably well. So this is what we're doing here. We're going to say this is the side or the direction of minimum overlap. And initially we give it as big a value as we can. We then check the top side, and we're looking here the amount of overlap between the top half of the second one, taking away the bottom half of the first one. So this gives us our amount of overlap from the perspective of it hitting from the top. Now, if it's greater than 0, so in other words, there is actually some overlap, they're not actually separated, and the overlap is the lowest amount of overlap that we've seen so far, then we remember it. We say that, okay, this is a top collision, and here is the amount of overlap. And we're basically doing that operation for each of the other sides. So from the left-hand side, we check then, we look for the right-hand side of this, take away the left-hand side, that's the amount of overlap on the left. Do we actually have positive overlap? In other words, has it collided in that particular direction? If so, is this the least amount of overlap that we've seen, which is what we assume has been the direction of impact? And if that's the case, then we update and we remember our minimum overlap. And we return it at the bottom. So this actually is sufficient to determine how we have come into collision, provided we've got a reasonably fast frame rate and provided the speed of objects is not excessive, and that'll be the case for 99.9% of games. So this one here gives you the type of collision, but it doesn't change any of the positions, it just works out what it is. The final one we have within this here goes further. It not only works out if there's been a collision and tells you about it, it also will resolve it. It will reposition the object so that it is not in collision anymore. So to do this here, we are effectively doing something quite similar. We're working out, okay, are we in collision? So do we have a collision? If we do, we're then going through our 4 checks again to work out how we are in collision. Is it along the top, the bottom, the left, or the right? And down here, we're separating, so depending on the collision type, if we're viewing it as a collision along the top of the object, then we will change the object's Y position to bump it up, so it's not in collision anymore with it. If it's a collision with the bottom, then again we're going to change the position so that it's just out of collision, and ditto for the right and ditto for the left. So this is the one here that actually takes the collision depth that we calculate and uses that to further update the location of the object so we don't have any collision. And that's all there is to it. It's reasonably straightforward, I think. It works quite well for platform games, because in platform games you generally do have rectangular bounds for the platforms or for the objects. If you're doing sort of a more of a top-down side-scroller one, easy enough to change all of this here to use spheres or circles, and you have more or less exactly the same principle. Collision resolution in this case is looking at, again, you would look at the direction they came together, you work out which object you're moving, and you would then move it along that direction by the overlapping distance, and you can use that then to separate out the two circles. So hopefully of use. Should cover most of the collision detection that we have or within our games.